picture this. It is like midnight.
Oh, the classic developer hour.
Exactly, yeah. The glow of the monitor is basically the only thing lighting up the room. You have your favorite caffeinated beverage right there on the desk, and you are just staring at a blinking cursor in your IDE.
We've all been there.
Right. You are a software engineer, and you are building an AI application.
Yeah.
And, you've got the front end looking super slick. Your API calls are routed perfectly. But there is this massive black box just sitting right in the middle of your architecture.
The infrastructure.
Yes, the actual physical silicon and the software layers that make these giant language models do their magic.
It's totally the great mystery for so many developers right now. I mean, we all know how to send a JSON payload, right? You toss a prompt to an endpoint and get a string back.
Sure, it's just a fetch request.
Right, but understanding what is physically happening over on that server rack to generate the response, that requires peeling back, well, layers of abstraction that most of us just rarely ever touch.
And that is exactly our mission for this deep dive. We are taking the material from the LLM Mastery Series today.
Specifically, their breakdown on GPU-accelerated AI with NVIDIA tools.
Yeah, which is actually the culmination of their whole building apps module. We're going to completely demystify the actual infrastructure that makes AI run so that you, the developer listening right now, can finally understand building, deploying, and serving these applications from the absolute ground up.
It's such a crucial piece of the puzzle.
It really is. And I want to set the stage right away with something that, honestly, completely caught me off guard in the material.
Oh, I know what you're going to say.
It's wild. The biggest hurdle in running a large language model, like the thing that basically dictates your app speed and your cloud bill, is it's not actually a computation problem at all.
Which, I mean, that feels completely backward.
Totally backward.
We are talking about the most complex computational models humanity has literally ever built. And compute isn't the bottleneck.
Right, so if it's not a computation problem, we really have to establish the baseline of what the hardware is actually doing down there. Because if you're going to understand the software tools we use to build AI, you have to, understand the metal it runs on first.
You have to know the silicon.
Exactly.
Yeah.
So why are we all completely obsessed with GPUs instead of our standard trusty CPUs for artificial intelligence?
Well, I mean, it really just comes down to the underlying math.
Okay, lay it on me.
When you strip away all that sci-fi anthropomorphism about artificial brains and, machines thinking.
The marketing speak.
Yeah, the marketing speak. Underneath that, a neural network's computation is fundamentally just massively parallel matrix multiplication.
Just grids of numbers.
Exactly. Grids of numbers being multiplied by other grids of numbers just
Right.
over and over again. When we talk about a model's weights or its parameters, those are literally just the numbers stored in the matrix.
And what about activations?
Yeah.
Because that always sounds so biological to me.
Right. It sounds like neurons firing.
Yeah.
But an activation is really just a software engineering state value. It's simply the numerical output of one math function that then gets passed as the input to the very next layer.
Okay, so let's actually put this into developer terms because, we are so used to optimizing for the CPU in our day-to-day. We want the fastest clock speed, right? The absolute smartest single-thread performance we can get.
Yep, the classic CPU mindset.
So think of a CPU like a single, incredibly brilliant senior engineer.
Oh, I like this analogy.
Right. This senior engineer can solve the most complex, convoluted logic problems you throw at them. They can execute code sequentially, handle deeply nested if-then statements, complex branching logic, and they do it incredibly fast.
But they're just one person.
Exactly. Just one super smart person. But a GPU, on the other hand, is like an army of thousands of junior devs.
Thousands of them.
Thousands. And they are not solving complex architectural problems. They can really only do basic arithmetic. But because there are so many of them, they do that basic math at the exact same time.
They do it in parallel. And, the historical accident of it all is just fascinating to me.
The video game thing, right?
Yeah. That army of junior developers, that architecture of thousands of simple cores working in parallel, it was definitely not originally designed for artificial intelligence.
Not at all.
It was built to push pixels to a screen. I mean, if you are rendering a 3D video game, you have millions of pixels, and you need to calculate the lighting, the shading, the color for every single one of those pixels completely independently.
And you have to do it 60 times a second.
Exactly. And you don't need one genius processor to do that sequentially because, Pixel A really doesn't care what Pixel B is doing.
Right. They're independent.
Hmm.
You just need thousands of tiny processors doing basic math simultaneously.
And it turned out, and this is the crazy part, that the exact mathematical operation required to calculate how light reflects off a virtual polygon in a video game.
Yeah.
It happens to be the exact same mathematical operation needed to calculate the weights and activations in a neural network.
That is just such a wild coincidence.
It really is. The hardware architecture was just already built. It simply needed to be repurposed. CPUs handle the complex sequential logic, but for AI, we just need raw, overwhelming parallel scale.
Okay, so if the GPU is this massive army of thousands of workers calculating in parallel, you would naturally think that making an AI faster just means, well, giving them more math capability, right?
That's the logical assumption.
Yeah.
Add more workers, get faster math.
Exactly. But the source material points out that for large language models, inference, which is, the act of actually generating the response, is typically not compute bound at all. It is memory bandwidth bound.
Yeah, this is the big plot twist. The GPU can actually perform the matrix calculations much, much faster than it can physically read the model's weights out of the memory chips.
Wait, so it's literally just a massive traffic jam.
It is entirely a traffic jam.
It's like having a world-class chef who can chop vegetables in like a microsecond, but you're making them wait for a waiter to slowly walk over and hand them one single carrot at a time.
Yes, that is exactly it. And the chef isn't the bottleneck there, the waiter is.
Oh.
And that reality completely changes how you have to architect your entire system. The bottleneck isn't the brain doing the thinking, it's the nervous system delivering the data to the brain.
Because an LLM has, what, billions of parameters?
Billions. And to generate a single token, just a single word, the GPU has to pull almost all of those gigabytes of weights from the VRAM, the video memory, across the physical motherboard bus, into the processing cores, do the math, and then
And then it has to do it all over again for the very next word.
Exactly, because it's an auto-regressive process.
Right. It predicts the next word based on all the previous words. So for every single word it spits out on your screen, it has to load the entire massive model into the active processing cores again.
Every single time.
As a dev, that's like an API timing out while waiting for a database query, but it's happening billions of times a second on a microscopic level. That is wild.
The compute cores are literally sitting completely idle for microseconds, which, is an absolute eternity in computing time, just waiting for the data to arrive.
Okay, so if the hardware is fundamentally starved for data, we obviously can't fix that with a soldering iron. We have to fix the traffic flow using software. Is that where the whole NVIDIA layered software stack comes in?
Precisely. Because raw silicon is completely useless without instructions that know how to exploit its specific architecture.
Right.
NVIDIA didn't just build the hardware, they built an entire ecosystem of software layers to manage this exact memory traffic problem.
Okay, let's ground this in a practical engineering reality then. Don't just list the stack for me. Let's actually trace a single API request.
Sure, let's do it.
Say I have a React app, right? The user types a prompt, hits submit, and sends a JSON payload to my server. Walk me down the stack. What actually catches that request first?
The very first layer your request hits is Triton.
Triton, okay.
Yeah, Triton is the inference server sitting at the very top of the stack. It handles serving the models at scale. If you have, say, 100 users all hitting submit at the exact same time, Triton manages those incoming requests.
Like a load balancer kind of thing.
Sort of, but here is the really brilliant part. To solve that memory bottleneck we just talked about, Triton does something called dynamic batching.
Dynamic batching, what does that look like?
Well, it might actually hold your specific request for like 20 milliseconds just to group it with 5 other requests that just came in.
Oh, I get it. Because the trip across the memory bus is so ridiculously expensive, it's basically telling the waiter to carry 6 carrots at once to the chef.
Exactly.
Rather than making 6 totally separate slow trips.
You're maximizing the data payload for every single memory read. So once Triton batches those requests together, it hands them down to the next layer, which is TensorRT.
TensorRT, I've seen that acronym everywhere.
You definitely have. It's the optimization layer. It takes the neural network model and mathematically reorganizes it to run as efficiently as physically possible on your specific GPU.
Okay, I want to dive really deep into how it does that in a minute, because the material makes a big deal out of it.
Oh, it is crucial. We will definitely get back to it.
But just to finish the stack, so Triton manages the network traffic and batching. TensorRT manages the optimized execution graph. What is sitting below that?
Underneath TensorArt sits CUDDN. That's the CUDA Deep Neural Network Library.
CDNN. Okay, what does that layer do?
This layer adds highly optimized deep learning primitives.
Primitives. Wait, what is a deep learning primitive in normal software engineering terms?
It is essentially just a standard library of math functions.
Oh, okay. Like standard library stuff.
Yeah, imagine you're a framework developer, like the people building PyTorch. Instead of you having to figure out how to write a pooling function or a forward convolution from scratch, CuddyNN just provides it out of the box.
Right. And pooling is just, that's downsampling a data matrix to save processing power, right?
Exactly. And normalization is just scaling data to a standard range. NVIDIA has already written the absolute most mathematically optimal hardware-specific version of those functions for you.
Nice. So CuddyNN is the standard library.
Mm-hmm.
And below that, the metal.
Well, one more software layer, the Bedrock Foundation, CUDA itself.
Ah, CEA.
CUDA is the parallel computing platform and programming model that allows software to talk directly to the GPU cores. It is essentially the assembly language of NVIDIA GPUs.
So this is what's actually managing the memory allocation on the physical hardware level.
Right. It tells specific physical cores what to flip. Most application developers, building everyday apps will never write a single line of raw CUDA code.
Yeah, I certainly haven't.
But every single layer above it relies entirely on it to actually move the electron.
Man, we just went from a web request and a React component all the way down to flipping silicon registers. That is so cool.
It's quite the journey.
But let's actually go back up to that optimization layer, TensorRT. Because the LLM mastery breakdown makes it extremely clear that out of this whole stack, this is the one layer software engineers deploying AI absolutely must understand.
Without a doubt, it is the single highest impact step between training a model and deploying it in production.
They say it routinely provides a massive 2 to 5 times speed up in production inference.
It does. It's incredibly powerful.
Okay, I have to call a timeout here. Seriously. A 2 to 5 times speed up just from a software layer.
Yep.
Without retraining the model at all, without changing any of the weights. How is that physically possible without just breaking the AI? Are they just like caching the data closer to the processor so it doesn't have to cross the motherboard as often?
Well, the material mentions something called layer fusion.
Layer fusion. Okay, how does that work?
Well, you've essentially just described exactly what layer fusion is doing with your caching guess. In a standard neural network, you have multiple layers of sequential math operations.
Okay.
Say you have operation A, operation B, and operation C. Normally, the GPU reads the data from the slow main memory, performs operation A, and writes the intermediate result back to memory.
Right.
Then it reads that result from memory again, performs operation B, and writes it back. Then reads it again for operation C.
So every single read and write is a completely separate trip across that slow memory bus.
Exactly.
You are basically making the chef wait for the waiter 3 completely separate times for one dish.
Right. So what layer fusion does is it analyzes the execution graph and realizes, hey, operation A, B, and C always happen sequentially anyway.
So it groups them.
It mathematically fuses them into a single operation kernel. So now the GPU reads the data from memory just once.
Oh, wow.
It performs A, B, and C while the data is sitting right there in the ultra-fast localized registers directly on the processing chip, and then it writes the final result back to memory once.
You just completely eliminated 2 full round trips.
Exactly. It's a massive time save.
That makes perfect sense. It's honestly just like avoiding database writes for intermediate variables by keeping them in local memory until your final calculation is done.
Perfect analogy.
But the material also mentions this other thing, precision calibration. My guess is this relates to the actual data types we are using for the model weights.
Spot on. So during the training phase, neural networks typically use 32-bit floating point numbers.
Which are huge.
They are very precise, but yeah, they take up a ton of memory and, crucially, a ton of bandwidth. So precision calibration safely reduces those numbers down to 16-bit or even 8-bit integers for the inference phase.
Okay, so if I'm sending an array of 8-bit integers over a network bus instead of 32-bit floats, my payload is a quarter of the size.
Right, exactly.
It directly attacks that bandwidth bottleneck because you can shove 4 times as many weights across the memory bus in the exact same amount of time.
Yes. And the cool thing is, because a neural network is fundamentally a probabilistic model anyway, it is surprisingly resilient to slightly less exact math.
Really? It doesn't hallucinate more?
Yep. Not noticeably, no. Losing a tiny fraction of mathematical precision by rounding a 32-bit float down to an 8-bit integer usually doesn't ruin the output at all. The language model's response is practically identical, but the hardware runs phenomenally faster.
That is so clever, just chunking it down. There is the third optimization mentioned, though. Kernel auto-tuning. Does TensorT test this in real time while the model is actively running?
No, it actually profiles the hardware ahead of time.
Oh, ahead of time.
Yeah. Before you deploy, TensorT looks at the exact specific GPU model you were using. Say, an enterprise A100 versus your consumer 4090 at home.
Okay.
It tests dozens of different micro-level execution strategies and memory allocation patterns to see which one runs fastest on that exact chip's unique physical architecture.
Wow.
And then it compiles a highly optimized engine specifically locked to that piece of hardware.
So if you don't use TensorT, you are essentially leaving, what, 80% of your hardware's performance completely on the table simply because of traffic jams and inefficient data types.
Pretty much, yeah.
That completely demystifies the software side for me. But the final piece of the puzzle here is the physical metal itself.
The hardware.
Yeah. If I'm a developer, what actual physical hardware should I be running this whole optimized stack on?
Well, the hardware scale progression directly tracks with your deployment journey as a business.
Okay, walk me through it.
If you're just prototyping an app in your bedroom, experimenting with the architecture, the baseline is consumer-grade hardware, specifically the RTX 4090 or the upcoming 5090 series.
Yeah, the 4090 is basically the ultimate developer sandbox right now.
It really is.
It has 24 gigabytes of VRAM, which is enough to load small to medium open source models natively. You can just write your inference code, test your Triton batching, compile your Tensor engines locally without burning through hundreds of dollars in cloud compute credits.
Exactly. It keeps development cheap. But once you move from your local machine to actual users, the demands change entirely.
Right. Bedroom to startup?
When you become a startup, when you have concurrent users hitting your API 24 hours a day, you have to move to the cloud. You transition to enterprise-grade silicon, like the A100 or the L40S.
So what actually makes an A100 different from my local 4090, other than the massive price tag?
Massive memory bandwidth.
Back to the bandwidth.
Always back to the bandwidth. The A100 uses a totally different type of memory called HBM, or high bandwidth memory, which is physically located much closer to the processor.
Oh, so a shorter walk for the waiter.
A much shorter walk. It is designed specifically to alleviate that exact waiter and chef bottleneck we keep talking about. And they are also designed to run at maximum thermal load constantly in a server rack, which, consumer cards will definitely struggle with over time.
They'll just melt. Okay, and then you hit the big leagues. Global scale. Millions of users.
Right. For massive deployments, think thousands of concurrent requests per second, you are looking at dedicated H100 clusters?
Clusters.
Yes. And at this scale, a single GPU simply doesn't have enough memory to hold the massive frontier models we are seeing today.
So you have to split the model across multiple GPUs. But wait, if the bottleneck is memory bandwidth on a single motherboard, you can't just slap two GPUs on a standard PCIe server board, right?
You can't.
Because the motherboard itself would just become the new traffic jam trying to pass data between the two chips.
Exactly. And this is where NVIDIA's NVLink comes in.
NVLink?
NVLink is a custom, massive hardware bridge that physically connects the GPUs together. It provides such a ridiculously wide data pipe between the chips that multiple H100s can essentially share their memory bandwidth natively.
Oh, wow.
To the software stack, a cluster of H100s connected by NVLink basically acts like one giant, unified superchip.
So you really just scale the metal to the mission. You start on a 4090 to build it, you deploy on an A100 in the cloud to test it with real users, and then you scale to the world on an interconnected H100 cluster.
That's the playbook. And, this progression really ties a neat bow on the overarching building apps module we've been covering from the LLM Mastery series.
It really does. I mean, we have looked at how to route requests using APIs. We explored the flexibility of open source models versus proprietary endpoints.
We discussed the cost-saving power of small, specialized models, too.
Right. We addressed the critical importance of security and data privacy, and we touched on the unique user experience challenges of generative UI.
And now, by finally understanding this underlying GPU infrastructure, from the massively parallel math to the memory bottleneck, to the way Triton and TensorArt optimize the traffic flow, all the way down to the physical silicon, well, you finally have the complete picture.
You can build, deploy, and serve AI applications totally end-to-end.
Which is huge.
The transition from high-level theory to physical application is always the absolute hardest part of software engineering. So it's just incredibly empowering to see the whole stack, from the front-end user click all the way down to the electrons moving through the CADA cores.
It's all just one continuous pipeline.
So to summarize our journey today, we started with the fundamental reality that AI is really just massive parallel matrix multiplication. We discovered the hidden trap that inference is bound by memory bandwidth, not compute speed.
The waiter is too slow for the chef.
Exactly. We decoded the NVIDIA software stack, learning how Triton batches requests, how Tensor fuses layers and reduces precision, and how cuDNN and CADA physically execute the math. And finally, we mapped out the hardware progression.
Understanding these underlying mechanisms makes deploying AI entirely manageable. You aren't just sending API calls into the void anymore.
No, you actually know what's happening. But before we sign off, I do want to leave you, the listener, with a final thought to chew on, something that builds on everything we've explored today.
Oh, a provocative thought. Let's hear it.
We just spent this entire deep dive looking at how incredibly fast and powerful AI can be when it utilizes this massive speedup from TensorArt, relying on the deep foundations of CADA, running on interconnected hardware like NVLink. But here's the catch. That entire layered stack, top to bottom, is built specifically and exclusively on NVIDIA's proprietary ecosystem.
Ah, yes. Vendor lock-in. The entire industry has heavily optimized for one specific company's hardware architecture.
So what does that mean for the future of the software engineering industry? If the whole AI software world, every single framework, every optimization technique, every deployment pipeline is this deeply entrenched in NVIDIA's specific way of doing things.
Right.
Could the very optimizations making AI incredibly fast today become the exact chains that prevent entirely new non-GPU architectures from breaking into the market tomorrow?
That's a scary thought.
Right. If a startup invents a radically different, fundamentally better microchip for AI next year, will the software ecosystem even be able to pivot to use it? Or are we just locked into this specific compute paradigm for the next decade?
It is the ultimate double-edged sword of intense optimization. When you build the absolutely perfect road for one specific type of car, no other vehicle can drive on it.
Yeah, exactly. Something to definitely think about the next time you are sitting there watching your code compile.
For sure.
Thank you so much for joining us on this late-night journey through the silicon. We hope you finally feel equipped to untangle that infrastructure black box. Keep building, keep optimizing, and remember to make sure your chef always has a steady supply of carrots. We'll catch you on the next deep dive.